In this review of the basic concepts of probability, we would like to cover the three approaches to defining the concept, the three axioms of probability, some applications of the counting principles, probability of joint events, the concepts of conditional probability and statistical independence, the theorem of total probability, and Bayes' theorem. And as we'll usually do, solve examples during the lecture. These three texts will serve as further reading. The book by Sheldon Ross, the book by Papoulis, later revised by Pillai, and once again the book by Sidney Resnick. Now, why do we need to define probability? We might find ourselves in a situation, as we saw in the first lecture, where we need to infer the properties or the state of a system, or to predict the outcome of a future event, or to judge the truth of a hypothesis or the accuracy of a model. The problem is we lack complete certainty. We do not have all information about the quantities we are trying to define. But what we do have is access to thought experiments or access to actual experiments under nominally identical conditions repeated many times, or some understanding of the context of the problem and experience with similar situations. Now, let me pose three questions, and these would actually give rise to the three definitions of probability that we use. The first one is, there is a fair die, I want to throw it, how likely is a 6? Now, this represents a vast number of problems, and I have listed just a few. The second one is the die is loaded, how likely is a 6? And again, this represents a large class of problems, and I've listed a few examples. The third question sounds similar, but each is subtly different from the others. So this one is, there is an assertion that this die is fair. Now, how likely is that assertion to be true? This also represents a wide class of problems. I've listed just a few examples. Now, in the first example, we can take advantage of the fact that all the outcomes are equally likely because the die is fair. There are 6 faces, so the probability of getting a 6 is 1/6. And this constitutes the classical definition, which involves thought experiments but requires, as I said, the outcomes to be equally likely. In the second one, I do not have the advantage of equally likely outcomes, so I have to resort to experiments. I need a large number of nominally identical trials, and then I can estimate the probability. This is the frequentist definition of probability. Now, in the third type of problem, I may not even have access to experiments. I may have access to some data, but I have understanding of the problem, its context, and I might have experience also. So in that particular case, I can set up the hypothesis, I can perform some tests, and I can say that I'm 50% or 90% or even 100% certain that the die is fair. But I will have to bring in my judgment and my value system and how much I trust the data, the experimenter, or the model. So the question is that whichever way I define probability, are these approaches compatible with each other? And if I have a problem that involves two or more such definitions, can I mix them and get results? The answer is yes, provided your definition satisfies the three axioms of probability. So we have a probability space consisting of the sample space, an appropriately defined algebra defined on the sample space, a collection of subsets of omega, and an appropriate measure defined on that collection, which we call probability. So it's non-negative. That's the first axiom. The second axiom uses normalization. So the probability of the sample space, the shear event, is 1. And the third axiom says that probability is additive in nature. So if I have a finite or a countably infinite collection of sets in F, the probability of the union is the sum of the individual probabilities.